Thank you. I'd also like to thank our hosts and sponsors here for giving me the opportunity to present this. It's the geothermal paradox, or what I like to call the one big beautiful paradox. And what it posits is that even though geothermal energy is only 0.03% of the total global energy budget, it's small, it appears to have had a significant impact on the Earth's recent temperature changes. And we're going to present some theoretical information, some observational information, and some statistical information to prove the point. Increasing geothermal heat flow strengthens the oceanic convection while intensifying the transport capacity of the ocean currents. Now, why is this important? The oceans contain 1,000 times as much energy as the entire atmosphere does. In fact, the top 3 meters of the ocean contain as much heat as the entire atmosphere does. So this is a massive reservoir of heat, and if you get it to move around a little bit and to somehow amplify heat exchange for different parts of the globe, it does make a difference. Now, 80% of the Earth's geothermal heat has its origins in the submarine volcanoes and hydrothermal vent fields. We see the hydrothermal vent fields here on the left-hand side. These are, we've all seen these National Geographic things with the gummy worms and all kinds of strange things crawling around out there. Temperatures coming out of these vents get up to 400 degrees Celsius, or about 750 degrees Fahrenheit. The underwater volcanoes, they're a little bit warmer. They get up to about 2,200 degrees Fahrenheit. So we can get some significant convective activity as a result of this. Now, here's a map of the zones where most of this geothermal heat is being realized. The largest area is off the west coast of South America. This is called the East Pacific Rise. The East Pacific Rise is a spreading area. It's an area where the crustal plates are being pulled apart. The Pacific Plate, for example, which is, of course, to the west of it, is being moved about 3 to 4 inches per year. That includes the plate, the lithosphere, and all the water that's on top of it. We also have the Mid-Atlantic Ridge here, which is the longest one. And then we have the Indian Ocean complex here, which comes down to the Mid-Atlantic Ridge, the Mid-Indian Ridge, and the Antarctic complexes of the Pacific and Indian Ocean. Now, as reported by Davis et al., and this is sort of a founding principle here, seafloor hydrothermal systems are known to respond to seismic and magmatic activity along mid-ocean ridges, often resulting in locally positive changes in the hydrothermal discharge rate and temperature. So, what we have here is a founding principle. That is, whenever we have an earthquake, when we have seismic activity in these spreading zones, we're going to see changes in the temperature because these magmas come out pretty hot. Here we see a box diagram of this. We have our magma chamber down here. These are basaltic magmas that get up to, as we said, about 2,200 degrees Fahrenheit or 1,200 degrees Celsius. Now, they refer to this as a mid-ocean ridge. The mid-ocean ridge is actually part of a larger complex that I'm calling the spreading zone centers. And earthquake frequencies in these mid-ocean spreading zones thus provide us with a proxy for geothermal heat release. That is, the more seismic activity we see in these spreading zones, the more heat that's being released to the overlying ocean above it. Now, we've developed a 4-point flow chart for this geothermal paradox, and hopefully we'll walk you through this step by step. Increased geothermal heating in mid-ocean spreading zones will be driven by higher seismic activity in those areas. Let's see if we have, in fact, had more seismic activity in these mid-ocean ridges or these mid-ocean spreading zones. To assess this, we're going to use what is known as the GCMT catalog from Columbia University. It's the Global Centroid Moment Tensor Catalog. It is considered to be the highest quality seismic database in the world. They look at mid-size and large earthquakes, and they have what is called a magnitude of completeness of about 5.3, going back to the mid-70s. That is, they've recorded 100% or nearly 100% of all the earthquakes going back to the mid-70s. And this is really important. We want to make sure that we minimize sampling errors if we're going to be sampling the number of earthquakes that we've had. Here are a couple of references on this point. And in fact, if we graph what I'm calling MOSIA, mid-ocean spreading zone seismic activity. This is a nota bene, as they say in Italian, note this well. The mid-ocean spreading zone seismic activity, we see that there has been an increase starting down here in 1977. We start our time track. It moves up nicely. We see a big jump up that starts in 1995. I think Judith Curry talked about that today. And then we see another jump up going here in 2007, 2008. The 2005 data hasn't been completed yet. They run about 4 months behind to complete this catalog. So we're seeing that, yes, we've had a 5-fold increase from 1977 all the way up to 2014 is the high point on that, to about 108. Now, people say, look at the graph. Well, look at the frequencies are very, very low. They're like sunspot numbers. However, that's for the earthquakes 5.3 and higher. The entire envelope goes down to a seismic reading of 1, and it's a logarithmic relationship. So all of these numbers here, to get the entire seismic envelope, is times 10 to the 4th. So we're talking about 220,000 here and a little over 1 million here. So we got to keep that in mind. A lot of seismic activity. Now, so we've shown that there has been more seismic activity, or MOSIA has gone up. We can assume that greater geothermal heat flow will then result in more ocean convection plus stronger currents via what we call an intensified thermohaline circulation. And this is the key to this whole thing, this thermohaline circulation. Let's look at first the convection. And according to Model and Wheat, thermally driven convection of seawater occurs through oceanic crust of all ages. Most of the hydrothermal heat loss occurs on the mid-ocean ridge flanks. That's these spreading zones. As I said, I used the more comprehensive term. The estimated heat loss on the flanks is so large that upwelling must occur over a large fraction, 5 to 30% of the seafloor that's less than 65 million years in age. This is critically important. There's a lot of water sitting on top of these spreading zones. It takes a tremendous amount of heat to get it to convect. But there's enough heat, as I said, when you get up to 2,200 degrees Fahrenheit, you can convect these things. You can see that we have a large area of ocean. The reds, orange, and yellows are less than 65 million years of age. The vast majority of the ocean crust is less than 65 million years of age. 5 to 30% of that will get convection. All right, and convection at the bottom is critically important because that drives what we call the thermohaline circulation. And now we'll describe what that is. So, according to NOAA, they describe the thermohaline circulation as a process driven by density differences in water due to temperature and salinity variations in different parts of the ocean. It's also called the ocean conveyor belt. Here we see a bird's eye view of the thermohaline flow in the Atlantic. This is called the Atlantic Meridional Overturning Circulation, or AMOC. This is a critical component, a critical driver of the ocean circulation. And we see down here upwelling of bottom waters in Antarctica. This is due to what's called diapictal mixing. It then becomes a surface current that moves up through the entire Atlantic basin. And then we see downwelling off the coasts of Iceland and Greenland. And this downwelling is a critical driver of the thermohaline flow. Here we see a side view of this. This is the Atlantic circulation. We see here the upwelling of what's called the North Atlantic deep water off the coast of Antarctica. It then migrates through the tropics in the Atlantic basin, picks up heat, and then by the time it gets to mid-latitudes, it starts to lose heat. And as it loses heat in the Arctic region, it gets colder, and if it gets cold enough, it starts to freeze. And this is when the party starts. If you start to freeze seawater, the ice is rejected from the crystal matrix. What's left is fresh water. All icebergs are fresh water. And what you're now left with is a very, very cold and salty water that will sink rapidly. This area here in the Arctic is referred to as the chimneys. The chimneys displace an incredible amount of water. about 1 billion cubic meters of water per minute go down the chimneys, which is about 20 times as much as the total output of all the Earth's rivers. So there's a tremendous amount of water being pulled down to become the North Atlantic deep water, in which it then circulates back up and comes back. This entire thermohaline cycle is what is referred to as deep convection. Here we see the entire picture. We see upwelling in both the Pacific and Indian Ocean, and then we see the downwelling here in the Atlantic Basin. This circulates the water over a period of about 1,000 years. Now, the critical part of this is that it doesn't move at the same speed. It varies. So, there's an extensive literature on the impacts of underwater geothermal heating on the thermohaline circulation. Here's a citation from Bellarata and colleagues. It is shown that ocean geothermal heat is a significant forcing that can weaken the stability of the water column, i.e. causing convection, warm the bottom water, and strengthen the thermohaline circulation. That is, this entire flow speeds up. Now, you say, well, that's just one article. What's the big deal on that? Do we have to really believe it? Well, here's 8 more of them, all peer-reviewed articles in top-flight journals, Journal of Geophysical Research, Geophysical Research Letters. And here's 8 more. We're up to 16. I could have expanded this out a few more pages. There's an extensive literature on this that has been completely ignored by the climate community. They don't want to hear about this stuff. So here we have a strengthening of the thermohaline circulation will then intensify ocean currents at all depths. Here we have what I call the 3 amigos. That is, according to NOAA, ocean currents are driven by wind, water density differences, which is the thermohaline flow, and tides. Okay? Tides, number one, we can cross this off the list because these are constant. We predict tides years out into the future. Tidal tail. Any fishermen here, you know that they have tide tables. They go out, I think it's 2 years. It's a constant, okay, for the time frames that we're dealing with. Winds, of course, are highly variable. Thermohaline is also highly variable, as we saw from the Mosier graph. Strengthened currents will transport more heat from the tropics into the Pacific and the North Atlantic and the Arctic. And these are critical regions. The Arctic has warmed the fastest. That's called the Arctic amplification. The second fastest regions are the North Atlantic and the Pacific, and the third is the tropics. And we're going to show how it all ties together now. So here we see the thermohaline flow in the Pacific. We have a long fetch along the equatorial regions here, and then it runs into a thing called Southeast Asia and Australia. And here we have 2 continents coupled with a series of archipelagos that bottle the water up. That is, the water reaches a choke point. And this choke point forms what we call the Western Pacific Warm Pool. This Western Pacific Warm Pool is a critical feature of the oceanic circulation. And we can see that over time, this Western Pacific Warm Pool has gotten bigger, it has gotten warmer, it has gotten deeper as the thermocline has deepened, and it has also gotten bigger. Sea level has risen in this area. So, the excess heat from this expanded Western Pacific Warm Pool is then pushed eastward by the Kuroshio current and the Kuroshio extension, first northward and then eastward. These are the equivalents of the Gulf Stream in the Atlantic. And as we say here, the Kuroshio and the Kuroshio extension, I'll show you a map in just a second, are warming 2 to 3 times faster than other areas of the ocean. The Kuroshio current extension is also shifting northward and increasing its transport capacity. In other words, it's pushing out more water and it's pushing out warmer water. Here we see the Kuroshio current here. Here we see the Kuroshio extension up here. And we can see here for June of 2023 a nice expression of this. We see that this area has warmed up very, very nicely. The North Pacific stands out. This is a semi-permanent feature now that we've been seeing in recent years. Let's take a look at the Kuroshio complex here. This is from Climate Reanalyzer. We're going to see what's going on in this area. Remember our 3 amigos, tides, constant, wind, thermohaline. Wind speeds have been going down. So if wind speeds are going down and tidal forces are constant, The only thing that can strengthen that is thermohaline intensification. That's the only thing that's left. We also get increased convection in this area. Off the east coast of Kamchatka, we have what's called a forearc basin that puts out a tremendous amount of geothermal heat. It's a shallow continental shelf that's only 600 meters in depth or less, and it generates a number of hotspots. I wrote a short article on this about the geothermal hotspot back last summer. Thanks to Joe Bastardi, he pointed this out, said, hey, you got to take a look at this. And according to Google Gemini, hydrothermal activity off the east coast of Kamchatka is characterized by intense, ongoing, geologically complex, high-temperature submarine systems. The region contains over 30 active volcanoes and approximately 270 hydrothermal vents. The water that gets heated up off the coast of Kamchatka will be pushed southward, where it hooks up with the Kuroshio, and here we will push it out into the middle Atlantic. We have this nice triangular-shaped region off the east coast of Japan, and let's see what happens in a case study for August 12, 2025. We see that this region was subjected to over 2,000 seismic events. That's 70 events per day, or a seismic event every 20 minutes. The area lights up like a Christmas tree. And you can see the entire Pacific Basin has lit up as the North Pacific Current pushes it around. This is a semi-permanent feature of the Pacific. As the geothermal activity increases in this area, we see the Pacific actively warming up. In the North Atlantic, we see a similar situation, but here the flow is what we call meridional. That is, it goes from south to north. Here we see the Gulf Stream, okay? And here we see the North Atlantic Current. And like its Western Pacific counterpart, the Atlantic also has a warm pool. It's called the Atlantic Warm Pool. And what's been happening to the Atlantic Warm Pool? The Atlantic Warm Pool has also been expanding. It's been growing at a rate of 500,000 square kilometers per decade. That's over the last 40 years. And the Gulf of, it's called the Gulf of America now, sorry, has experienced an acceleration of sea level rise between 2010 and 2020. A study by Smedzrud demonstrates that North Atlantic transport has increased significantly since 1900. A more granular study by Ozil using satellite-derived altimetry observations revealed an increase up to twofold in North Atlantic current surface velocities over the last 24 years. This is the North Atlantic Current. It moves through the European Arctic corridor. It gets squeezed in. It's pushing more water into the Arctic. This process is very well documented in the literature. It's called Atlantification. The more water you push up from the Atlantic into the Arctic, guess what? You warm up the Arctic. You warm up the Arctic ice starts to melt, and you then kick in a feedback mechanism. Let's look at the area studied by Ozil from 1993 to 2016. This was their study area, and the wind speeds are down. So if the wind speeds are down, it's not the tides, it's not the wind speeds, it has to be thermohaline intensification. That's the only thing that can cause that. So, all of this, the expansion of these warm pools, the increased current velocities going to the North Pacific, the North Atlantic, and the Arctic results in higher tropospheric temperatures, higher sea surface temperatures, and less Arctic sea ice. And that less Arctic sea ice contributes to what is called the Arctic amplification. The Arctic, by the way, is cooling twice as fast as the tropics and 7 times as fast as the South Pole. All right, so there's a huge differentiation here. And here we see the curve of Moja, which is our mid-ocean spreading zone seismic activity. That's the blue curve. And here's the red curve, which is the lower tropospheric temperature. And with using a 2-year lag, we see a tremendous amount of coherence in these two data sets. The R value is 0.74. This is an incredibly noisy system. We have urbanization, reforestation, deforestation, afforestation, desertification, changing cloud cover, and yet the mid-ocean spreading zone seismic activity, our proxy for geothermal heat, is accounting for 55% of the variation in the lower troposphere. And this is satellite-derived temperature. We say, let's take out the land because that's a complicated, it's a confounding variable in this. With a 1-year lag, we see that our mid-ocean spreading zone seismic activity in blue and the sea surface temperature anomaly. We're looking at the sea surface temperature. Here we see an R value of 0.85. That is explaining 72% of the variation in sea surface temperatures. Finally, if we look here at Mosia and Arctic sea ice extent, here again, Mosia's in blue. This is Arctic sea ice extent. We see that it's a perfect, almost perfect negative correlation. The correlation here is negative 0.91. If a student ever came to me and said, I found something with a negative 0.91 correlation, I'd say, go back and redo the experiment. Something's wrong. It's too high. We can invert that and say the inverse of Arctic sea ice extent is the amount of Arctic region that becomes ice-free. That is the ice-free Arctic, and flip it into a positive correlation with no lag, and it's practically a 1-to-1 correspondence. Here are critical summary statistics. This is the last slide. We can see the R values here, very, very high. This is the number I particularly like. This is what's called the p-value, for all you statistics junkies out there. This is the probability that the relationship between Mosia and lower troposphere temperatures is about the same probability of you winning the Powerball lottery with a single ticket. Here we can see the correlations are higher with sea surface temperatures, very small numbers. That has 11 zeros before you get to a real number. This one for Arctic sea ice, that has 16 zeros and then an 8. In such a very noisy system with lots of feedbacks, all sorts of things going on, we're getting extremely high correlations here that are highly significant. In fact, in the statistical literature, they talk of highly statistically significant, and that's what we have here. So, thank you.